So where we started from, we had a new Linux high-performance computing skunkworks project. You know, very unofficial, we're looking into things. And then we had what several people call catastrophic success. The business loved it. They loved it so much they wanted more. And it went into production, despite the fact that it wasn't a production environment. The inevitable happened, and suddenly we needed monitoring added yesterday. As always, you know, they give you so much lovely notice for this sort of thing. So I went looking for solutions. You know, why didn't we just use what we already had? We're obviously a large company, we have monitoring. Well, the system we were using, which will remain nameless, had stability issues. It would crash, we had to have a master process that restarted it when it died. It had resource utilization issues, and that's a really unfortunate habit of eating all available virtual memory on the machine, which made several production jobs rather unhappy. Writing custom agents was really difficult. There was a C API that like 3 people had the secret archives for, and you had to go and send your request off to another group, and they'd get back to you in a year or so with the custom plugin maybe. And if you had to debug it, heaven help you. And also at the time, there was no support for the Linux platform we were trying to roll out, which was good because that gave us the excuse to not use it. So, you know, why did we decide to go with Nagios? Well, spending money on a new commercial monitoring system was going to be very difficult politically. We had one in-house, why are you buying another one? And all the usual machinations that go on in a large company for when you're trying to write a check, especially if it's for something like OpenView, which runs in the millions of dollars. At the time, in 2003, Nagios was the most mature of the solutions we could find out there. We asked around a fair amount, talked to various people, and they all basically said, yeah, if you're going to use one, this is the one that seems to work, you know, pretty well for us. And there seemed to be a good community support. A lot of people were using it, developing applications for it. There was a good ecosystem around it. So it was, you know, likely this product wouldn't evaporate in 3 months when people lost interest. So we tried it. And then the problem started. So it didn't perform as well as we needed it to. At this point, our 100 or so servers was growing pretty much as fast as we could get them racked. And it just wasn't scaling well. Configuration management was a big issue. There was, you know, wasn't a lot of availability solutions, high availability built into the product, and there were a lot of integration and automation things we would like to have it, you know, do that just hadn't been done yet because it was rolled out in, you know, 2 days. So the first problem we ran into are the performance issues. Nagios supports 2 different modes of operation. The default are what it calls active checks, where it basically does a fork and an exec to run a binary. The binary has an exit code, which it then parses, and a string that it reads to figure out whether things are good, bad, or indifferent. The most you can get out of Nagios prior to 3x, which is in beta right now, is about 3 checks per second. And in 3x, you get up to about 13 if you eat all 4 cores of a pretty studly quad-cores machine. Still not all that fast. Also for statistics, if you want to do trending for historical data, it did another fork and exec for every data point, which made it even slower. And the web UI, you know, slowed to a crawl as your configuration got complex. This did greatly improve in Nagios 2x, where they pre-parse the config file for the CGI scripts. In 1.x, the CGI script parsed the config file every click, which was not very fast, as one can imagine, especially if you have a couple thousand machines. So the configuration management problems were the standard ones you run into. The configuration files are very verbose. Even if you use templates, if you have a large environment, the config files are huge, and they mostly look like gobbledygook. Trying to read them and fix the right thing in the right place requires, you know, a pretty high level of expertise for the system. Syntax errors are far too easy. And you know, fortunately, Nagios will at least tell you what you did wrong when you run it in validate mode, but there was a lot of, you know, cycling of this, and since a validation check could take 5 minutes on a large config file, it made it rather unpleasant to edit. And also, keeping up with a really high churn rate in the list of servers and services we monitored became very expensive because every change took too long. And our growth rate was, you know, approaching vertical, and this just does not scale well. On the availability side, all the usual culprits, hardware and software failures, building power downs, patches and upgrade cycles, and who's going to tell you if your monitoring system is down? Because your monitoring system is down. And that would be bad. And for the integration automation requirements, we really wanted to tie into our existing alerting and escalation system. We have operations teams globally that have all sorts of escalation lists and policies in place. Porting all of this information to the Nagios escalation system would have been rather difficult, and as it turns out, not necessarily possible. We also wanted to be able to suppress alarms based on our existing maintenance databases. If we've already said this server is undergoing maintenance or this entire building is down for the weekend, we don't want Nagios sending alerts about things, and modeling the entire dependency tree is really complicated. So it's much easier just to have the alerting mechanism suppress the alerts by tying into our existing availability databases. We also really wanted provisioning to be automatic. That was a huge thing for us. Otherwise, managing this on 10,000 hosts is going to be a nightmare. We have to use the existing provisioning system to configure the host for monitoring, so this all just magically happens behind the scenes. If we add another 18 steps to deploying a new host, the user pushback would be very high, and for good reason. So, given all these terrible problems, what did we actually do? So we moved from active checks to passive checks. Nagios supports reading state from a named pipe. In tests I did just before this talk, as opposed to 3 active checks per second, we can get over 1,800 passive checks per second. This removes one of the major performance bottlenecks. We split our Nagios configs into multiple instances. So we actually run multiple copies of Nagios on the same server. We deployed high availability servers, running multiple instances of Nagios. We did a data-driven config file generation, so we actually leverage our databases to do all the config generation rather than doing the manual editing. VI is not your friend. Neither is Emacs. And we created a custom notification backend. Fortunately, notifications in Nagios are just executable with arguments, so you can do arbitrarily complicated things with it. So, first of all, the passive check solution. We want to move most of the work as much as possible to the clients. This is the traditional computer science scalability solution of pushing the computation out to the leaves. Don't do everything centrally, it'll be a bottleneck. We batched the server updates unless a state change occurs. So the client is monitoring all these various agents, and if the current state is the same as the last state, there's no reason to tell the Nagios server about it because nothing's changed. Now, you do have to phone home every so often to tell mommy you're alive. Hi mom, I'm fine, I'll be home at 10, But you don't have to do it for every 3 seconds. You're monitoring, your probe interval on your monitors does not have to be the same as the update interval to the server. Now, if the state changes, you obviously want to do an immediate update because you want to have as little latency as possible between fault detection and fault notification. But as long as it's same old, just every so often say, yeah, everything's still good, or still bad. We randomize the server update times to avoid spikes. You don't want every machine to try to phone home at the exact same time. So in addition to the configured interval for updating the server, you have a configured random offset period where it splays the updates within that period to spread out the load as evenly as possible. The results need to be queued on the server. Think of this as a print queue. You have one named pipe, or possibly multiple named pipes, but you have certainly contended resource. In the naive implementation where you try to SSH into the server and write your state to the named pipe, you have to get a lock, and you have all the race conditions inherent with trying to get a lock on a shared resource, and some client could be starved theoretically forever. In reality, it wouldn't be that bad, but still bad enough. So we had to implement a queuing system. And we also split statistics to go out to a different backend. We don't send the historical data through Nagios at all, because all Nagios is going to do is take the string, you send it, and then pass it to someone else. It doesn't interpret it in any way, it just copies it along, so let's eliminate the middleman. So here's the data flow. Your clients run an application we wrote called Nagios Agent. I know it's a really inventive name, but we're geeks, we're not all that creative sometimes. They all, every so often, do a TCP connection to the MonQ daemon running on one of the servers, or more than one of the servers, which then multiplexes the data out to multiple Nagios instances and multiple, actually only usually one stats backend. It could be multiple, we don't do that, but it's possible. So the other thing we did is run multiple Nagios instances. So instead of having one Nagios binary daemon running with a giant config file for everything, split it out into both administrative domains and into areas of interest. So if I'm responsible for, say, fixed income servers and someone else is responsible for equity servers, I don't want to see their alarms. I don't care if they have 40 machines down, they're not my machines. Likewise, say I'm an application developer and I'm responsible for some application that cares about 3 database servers and some middleware servers and a few other things. I don't want to see everything else. I just want to see my set of services. You can do this somewhat within Nagios with service groups and host groups, but it gets kind of complicated. And also splitting them up does greatly improve the web UI performance. It solves this issue with having to parse the giant config file every time, which again, it got better with 2x, but we were rolling this out in the 1.x time frame where that was just a killer. And also it allows per group customizations. So if you want a different style sheet because you don't like the color scheme, or more realistically in one of our examples, we had a business unit that wanted hyperlinks to their own back-end data sources for these hosts in the host status page. So you had a simple one-click click-through view of other data. You can do that without impacting everybody else. Everyone can have their own customizations and not step on each other's toes and not have the horrible shared outage maintenance window that you can never ever get because it affects everyone. Then we went high availability. This is probably the hardest thing we did. The other stuff was persnickety and painstaking, but this was actually hard. There's going to be a diagram on the next slide, so it'll be easier to explain with that. But we run multiple Nagios servers on different machines in different buildings to avoid single points of failure wherever all possible. All the clients update all the servers. So all the servers should have the current state at any given time unless they were just rebooted. Every server publishes a heartbeat through the whole infrastructure to its counterparts, and they all monitor each other. If you're not the primary, you suppress all notifications if the state of the heartbeat is okay. So as long as your partner is phoning home, you get all the state messages, but you don't send alerts for any of them because everything's good. Now the downside to this is if your masters get partitioned, where they can't see each other, but the client can see both of them, you'll get duplicate alarms. But we decided that duplicate alarms are better than no alarms, so we'd like to avoid that whenever possible, but short of some really complex quorum system, you can't do it. So here's the data flow. Did I mention this was hard? So as you can see, there's a heartbeat process that goes through MonQ to talk to Nagios, which then sends a notification to the foreign server's MonQ, which goes back to Nagios to set the state, and vice versa. There are also ping checks in place so that it can fail very quickly if the other box goes down rather than waiting for a heartbeat timeout. So if the box is dead, just give up, take over immediately. Otherwise, if it's pingable but the Nagios crashed or something, or MonQ crashed, you have to wait for the timeout interval. Importantly, when the box starts, Heartbeat does not immediately start publishing OK messages. For a configurable timeout period on first launch, it publishes warnings. Because given that everything's a passive check infrastructure, if your primary was down, it will not know the current state of the universe. It will be incorrect. So you let the secondary keep handling the notifications until one update cycle or two update cycles have passed. So you have a fair confidence that everyone's phoned home at that point and your view of the universe is indeed correct, at which point you go okay and you go green and take over from the secondary again. That delay is really important. Similarly, we actually have that delay in MonQ itself, where if you restart it, you're obviously out of sync and it will publish warnings with a countdown timer in the status field, so you can make sure that you don't start telling people about data that's really not accurate. Now, the other big thing we did is using data-driven configuration file generation. We have a bunch of host databases and provisioning tools already out there. So all we had to do really is add a couple extra fields to the systems we already had that say, do you want monitoring on this host? If so, what kind of monitoring do you want? And we leveraged our existing configuration management tool, CF Engine, to generate these config files on both the server and the client. This is important because it also makes sure that the client config and the server config stays in sync. If they diverge, you're going to have issues. So we have templates, much simpler templates based on our particular needs than the templates used in Nagios proper, that have magic data in them which trigger database lookups and then explode out into tons and tons and tons of service checks and host checks and all the other fun things in the Nagios world. They're mostly data-driven. There are a few threshold overrides that CF Engine manages for us in some cases where we haven't yet, or hosts are basically one-off. There aren't enough of them to have a class to generalize into a database type, at least not short-term. Eventually, everything migrates into the data model, but short-term, you may need to change a threshold on a machine now, rather than waiting for all the data model changes that would have to be done. So you can do a quick override in CF Engine if you have to. So we also did a custom notification backend to integrate with our netcool infrastructure, and all very boring. But it took a lot of back and forth with the operations team to make sure that we were setting all the right little flags so that everything came up properly, so that they actually treated the alarms as the proper severity and all the other mapping that has to be done. Not necessarily, was one of the issues that's not technically difficult but required a lot of coordination. And it's very important because it allows the Nagios alerts to be treated the same as the alerts from every other alarming system we have in the company. So from a support person's perspective, it's the same alert delivery mechanism, which matters a lot when you're trying to figure out who to call in the middle of the night for a Tokyo problem. We also added the alarm suppression based on as I said before, the existing maintenance window mechanisms we have. And we can also just use simple email. We actually do for most of our alerts, we actually send via email, not via the operations team, because we don't want to call out. We don't want a complex escalation tree to be followed. And we just want a notification. Here is a problem. It's not the end of the universe. You ought to know about it just in case. And we can actually batch those alerts into updates only once every time period, which helps a lot for, say, business units who want to get alerts about their systems but don't want their mailboxes to fill up when all 300 of their servers have the same error because someone screwed up an application config file. So they get one email saying, all 300 of these machines had the same error, which helps a lot. That's also not built into Nagios. The alert aggregation isn't really there, so we added that on as an extra step. This system is not perfect. There are design trade-offs we had to make. Batching your updates means you have a very slow detection, or possibly slow detection, of zombie hosts. So if they're pingable but not actually responding to user-level processes, say they're swapping themselves to death because they're out of VM, you won't detect this until a timeout period happens, which can be rather long. Now, this is a tunable thing. You can set your batch update interval appropriately for your environment, but it is a trade-off you make by, you get better scalability, but your latency goes up. Nagios' notification escalation doesn't really work well without active checks or with batch updates, because it requires multiple notifications to do the escalations properly. If you're batching updates, you only get a single notification, or one every half an hour. So the escalations are very limited. Now, in our case, we mitigate this by just sending one alert to our ops team and have the humans do the escalation based on our rotas. But this is a limitation in the current system where, unless you tune your batch update interval to be very low, you really can't use these facilities that are built in. It requires configuration management. If you don't have it, you can't do this. Now, you could do some very minimal configuration management just to manage the agent configs if you wanted to, but you have to have something. Since you're pushing all the decision trees out to the leaves, you have to manage the thresholds on every node. There isn't one central place that configures what your maximum load average is supposed to be. Every single host has to know its own config. And which services that host is phoning home about has to match which services Nagios is expecting that host to phone home about. This is really critical that you have some kind of configuration management system to keep all of this in sync. And obviously, the more complex a system is, the more bugs it has. The harder it is to manage. The likelier it is that it can be difficult to find out why an alarm vanished down the rabbit hole instead of being delivered like it ought to have been. And this is inevitable with any large system. When you have thousands and thousands of services being monitored, you have to make some trade-offs. So when we were designing Nagios Agent, we had some design criteria. It had to be lightweight. Our users had complained and loathed the old system because it would take their machines out. And so their attitude was rip the monitoring out. We don't want it. It causes outages. It's worse than no monitoring. So we had to prove ourselves to the business to say that, no, really, this new agent is very lightweight. Here are the statistics. It never went over 1% of your processor ever, and it never ate more than 100 megs of RAM. It had to be easy to write and deploy additional agents. One of the main drivers behind this is we couldn't do application-level monitoring. Our old system did systems monitoring, but systems monitoring only takes you so far. What we wanted to enable the application developers to do is to do application-level monitoring and end-to-end monitoring. Inject timestamps into your market data system and consume them, and monitor the latency of your market data feed through your entire network. This is a common thing that people do, and anyone who has that kind of system, if they're not doing it, ought to be doing it. And these are being done with one-off applications that didn't tie into anything else, and no one else could see them. And it was a bad system. So we wanted to make sure that it was really easy for people to do that kind of thing into the common framework so that everyone could consume those alerts. Avoid fork and exec wherever possible. They're resource intensive. Don't do it unless you have to. For systems monitoring, you frequently have to. If you have an HP system, there are custom binaries you run to monitor the health of the server, and it's a binary. You have no choice but to fork and exec it. But don't do it gratuitously. Keep it to a minimum. Don't make it mandatory. We had to support agent callbacks to avoid blocking. We tried to keep the API as simple as possible, and if you aren't going to do anything that takes a while, you only need 3 methods. It's really simple to write. But say you are going to run this third-party binary that's going to go and grovel around in your firmware until you answers, it might hang. And so you need some kind of callback mechanism to tell you when this other process you spawned has I/O for you that you have to process, and timeouts and all the other fun stuff. We need to support proxy agents. So a lot of systems, sadly, aren't customizable. You can't install your own code on them. The most common example in our environment is our NetApps. We can't run our own agent on the NetApp. It's not possible. But we don't want to go back to the active check performance issue we had with the original Nagios. So we allow certain nodes to be proxy nodes. They perform whatever checks they need to on whatever host they need to, But the API is rich enough that they can say, this result isn't for me, it's for him over there. So you can return results for non-local hosts, which was something we actually missed in the first round of developing this, but quickly became painfully obvious we needed. We also wanted to evaluate all thresholds locally and batch the updates, as I discussed previously. So here's a simple agent config after all of this evolution. And hopefully you can mostly read that anyway. Every agent has a class, which is basically the Perl module that you use to do the checks. There's an instance of that class, just a name for configuration file purposes, basically. It has categories, which basically says who cares about the results from this agent. And a set of arguments, basically, to initialize whatever thresholds or other data that agent needs to know that isn't hard-coded. So we have, in this case, two different agents, both being ping agents, but one of them is categorized as both the application developers and the SA's care. It's monitoring, say, your database server. The other agent is monitoring some London link characteristics that only the SAs care about. The application developers don't want to know about this. It's not their problem. So we have two different server instances, basically server client instances, effectively. They're both using MonQ. They have different categories because they're different. And they can have different arguments as well. So they connect to different servers, different queue numbers, whatever's required. So basically, they update different Nagios instances on the back end. So the app devs get their instance updated with just the data they care about, and the sysadmins get their instance updated with all the data they care about, which is different. This is another thing that we didn't have day one, which became painfully obvious in time that we needed. I tried to keep it as simple as possible originally and discovered that when you have a complex environment, complexity is inevitable. When I was designing MonQ, again, design criteria, it had to be fast. My initial design target was 10,000 hosts connecting to this server. This is nothing new. Anyone who's ever run a web server knows all the techniques you use to make this fast. Forking once per connection is not it. It had to be secure. This is going to be exposed to who knows what. So it had to both be secure in itself, and it also had to sanitize the input before Nagios saw it. Because the downside to Nagios' named pipe is that you can put all sorts of interesting commands down that pipe in addition to service check results. It had to accept data from the clients and dispatch them to multiple different output queues. So it went into multiplex. We didn't have to run one queuing daemon per shared resource. We wanted to actually have just one daemon running and allow a client to update multiple resources with one TCP connection. As we discovered when trying to figure out why we had no alarms once, it really needs to supply heartbeats to Nagios, so that Nagios can notice when MonQ stops running and then go and complain to someone. And also we supply queue depth statistics to our statistics backend, so we can make sure that Nagios isn't falling behind. We don't have queues backing up. When we're actually adding is latency statistics as well. We don't have that now, but it's coming. Now, they're saying these things evolved over time. These are not spring fully formed out of our heads in the perfect implementation. We started simple and added things as we found out we needed them. So originally, you can only have one agent. You have one ping agent that had to do everything. We discovered that didn't work well enough, so now we can have multiples. The whole agent instance to server mapping complexity was added fairly recently when we just tried to divide things up small enough to support application developer views of the universe. It got added when it came up. Shortly into the development process, we added automatic reload of the configuration files and on the agent modules. If they change, reload them. We also will re-exec the Nagios agent itself if it changes. Stat is a wonderful thing. we added stats collection. Originally this was just alarms. And then, after we received a few thousand alarms, people decided they wanted to know, if this was a sudden spike or if this had been growing slowly over time. And we went, yeah, that's a great idea. Damn, I have a deliverable. And most recently, I just added SASL authentication. Before, we were sort of like, yeah, it's coming from a Goldman machine. We're okay with that. We know it can't do anything bad. We already filter out anything unfortunate it can do. But as part of the stats collection, because it's auto-provisioned, we actually wanted to limit who can, eat your I/O and CPU resources on your host. On the server side, originally it was one monolithic instance. It worked fine for us for a while, and then we ran into the various server-size problems and outgrew it. Which, we sort of split into multiple instances based on administrative domains originally, and then later based on application groups. Did the whole high availability thing, much pain and torment. SASL again on the server side. And of course the monitoring of MonQ itself, some more automated service dependencies so you don't get alarms triggered because your infrastructure is down and all that stuff. That's what I call kudzu. This project started for one set of machines, fewer than 200 hosts. It became used by large sections of our environment. This is the standard maxim. When you write something, make sure it's production quality, because even if it will never ever be used for production, they swear it'll become production. Also, massively over-engineer it if you have the time to do so, because while they say today it'll only be used by 3 people, eventually 30,000 will use it. So you don't have to implement it for 30,000, but architecting it for 30,000 is probably a good idea. I thought I had massively over-engineered this, and then I saw what happened to it, and I was really happy. And also, documentation and internal consultancy were really crucial for user acceptance. As this has spread between multiple sysadmin groups, multiple application development groups, all of that nature, there's the inevitable pushback. This is weird, this is strange, this is new. What is this? Why do I care? Why do I have to use this? And so being really thorough in your documentation and providing internal consultancy for new users is really important for getting anything of this nature pushed out into the universe. So some stats. This is one of our servers. It's a HP DL385 first gen box, which is a dual 2.6 gigahertz Opteron, 4 gigs of RAM. Not the dual core server, it's just 2 cores, two single core processors. We're at Enterprise Linux 4, Update 4, Nagios 2.9, we're 1 rev down. 11 instances of Nagios, over 27,000 service checks, where the services are being checked mostly at 2-minute intervals on the clients. Over 6,600 hosts. We're at 10% processor and about 500 megs of RAM. So, the proof of the pudding is in the eating. So this is why we went to all this pain and torment. Before we were falling over at, a couple thousand services. So, stuff is coming up. Source code release, finally, only 2 years after I tried to get this done. It's in the works now. It's being code reviewed by other people internally, and I have to finish up, auto-confing MonQ because it's in C. And a few other things we have to just finish up and tighten up to make sure that it's, releasable. We have to get rid of the 3 or 4 Goldman-specific bits that aren't releasable. Sadly, our configuration management system is one of the things we will not be able to release. It's way too embedded with our in-house database. It's not generic, and the amount of work in making it generic would be prohibitive. And also new features coming up. Want to add encryption. Right now it's authenticated, but it's not encrypted. It's just a question of resources. Getting crypto right is hard and time consuming, and I'm smart, but I'm not that smart, and I need at least a couple weeks of solid time to work on that, and it just hasn't happened yet. We want to support for pulling the status instead of the current push, which we do, which is sort of antithetical to the design, but in DMZ environments where you don't want to allow, for InfoSec policy reasons, incoming connections, you have to do that. So we're going to have some sort of polling system. We really want to add statistical analysis to our agent framework as a common shared resource all agents can use. This is much harder than it seems. A lot of users have said, well, why don't we just say if at least 50% of the last n samples have been bad, then you alarm, otherwise don't. That's one way of doing it, and you run the numbers and run the use case scenarios, and you find out that that's mostly right, but not really. So we're working with some people with a much better stats background than I have, since I have almost none, to actually figure out what the right algorithms are to do the multiple data point regression analysis to figure out whether something is significant or not. So we're going to try and come up with probably 2 or 3 different most common cases where you want to do that kind of analysis and embed it as a shared resource where an agent can be stupid and just feed the answers into the magic black box and get a yes, no, maybe output. Yet more agent plugins. Obviously, there's never any shortage of things that need to be monitored. No matter how much we monitor, we need to monitor more. No matter how much we do trending historical data on, we never have the data we seem to need to figure out why the machine is slow today. We solved all of yesterday's problems are always different. I also want to add support for the traditional Nagios plugin, the old school fork exec, return and return code, print a line to standard out agent. Just to leverage the fact that there are lots of people who publish plugins on Nagios Exchange. While it's not the most efficient way of doing it, it has great time to market to download and roll it out in 10 minutes. So add support for that. It's not hard to do, so why not support it? We don't want to use that model. Whenever possible, we basically would reverse engineer the plugin and have it be a Perl module that doesn't require a fork and exec. But time to market is critical in our business. So the other thing I want to talk about, I don't have slides for, sadly, is our statistics backend, which I've been mentioning. This is one of the other things we had a hard time with. We looked at the existing systems, and they almost all required a priori knowledge of your environment, which is difficult. It's the same problem where your client configs and server configs have to be kept in sync all the time. And it just didn't fit with our environment very well. So we decided to do something more interesting. We limit who can talk to the servers and send self-describing data from the agents. The agents publish the sample interval and the data types with the data they send. When the stats backend receives this information, it auto-creates the time series for the data it just received. It's all based on an RRD backend, round-robin database, RRD tool for the people who want to Google if they don't know already. It's one of the common things used by MRTG and a bunch of other things. We had to implement some extra functionality, so if the sample rate changes, it requires that you recreate your RRD database and basically do an interpolation of the results into the new sample rate. The advantage of RRD is that it's a constant size database. It works by a cascading bucket system where you keep 500 samples of whatever resolution your data is natively in, and then you decide to keep another 1,000 samples of the next larger time period with whatever aggregation function you support, usually average, but also minima or maxima are very useful, and so on and so on and so on. So with a fixed data size, you can go back in time a pretty long way, and all that happens is as you get further and further back in time, your resolution goes down, which is fine, because it's very rare that you need 30-second samples for more than a month. But hourly samples can be really useful for 6 months, and daily minima and maxima can be really useful for 3 years. So we implemented the standard RRD tool back end, but did a custom front end to do the auto provisioning. This makes it very easy to roll out monitoring of some new type of statistical data you want to try to trend, even if it's only for 3 weeks. You have some particular performance problem you're trying to investigate, you whack together some custom code to instrument a bunch of stuff that you'll probably never run again, but because it doesn't require any centralized policy decision to allow you to record this, you can whack it together very quickly on one host, publish the data, and be able to view it. Which was that sort of agile statistics monitoring really helped us. And there's a price. Because we don't keep the client and server in sync, the server can have data that was used for 3 weeks and never used again. So we basically have to run some cleanup jobs if we find time series that haven't been touched in forever, or time series that are for hosts that no longer exist in our environment. We have policies for when to age them out. But there is some, again, trade-offs to be made there. But it does enable us to have very flexible, very fast time to market for problem analysis. So that's what we did. Hopefully, if you are interested in the source code, I will be sending an announcement when that finally happens, hopefully before the end of the year, but it might slip into January, to Nagios users and Nagios Devel. So if you're subscribed to either of those lists, you'll get the announcement when it goes out. And questions?
Microphone enforcer. Ooh, loud. Sorry. I actually have questions too. You mentioned that you send your Nagios alarms into Netcool and people deal with them there. I have a pretty good experience with Netcool. They acknowledge them and do stuff with them. Do those acknowledgements end up back in your Nagios environment, or?
No, there's no backwards flow right now. We don't actually, so this is a political structural issue. None of the sysadmins use Netcool. We have no access to Netcool. We can look at it, alert history via a web page, that's about it. It's solely used by the operations team to manage the alerts. So since we have no access to it, we don't do a reverse feed. It's not tightly integrated. So the ops, when they get a call, when the operation successfully manages to reach an SA and wake them up for a critical issue, ops will acknowledge the alert in Netcool. The SA will then acknowledge the alert in Nagios if it's not going to be fixed. So if they fix it, there's no need to acknowledge anything because it goes away. But if it's going to be a longer term issue, then they'll add a comment to the alarm field in Nagios.
Okay, thanks. Next question. If you were going to do this today, would you still use Nagios or would you do something else?
I know of no other open source tool that's better today. If I were to rewrite the code, I'd structure it a lot better, knowing what I know now. But fundamentally, the architecture is probably about right. We are rolling out OpenView now inside Goldman, and we have the same issues with it we've had with every other commercial monitoring system with a very heavyweight client. Because it tries to be all things to all people in one monolithic binary, it's very difficult to control the resource footprint of it. We've had, again, issues where it caused performance impact that almost cause us to violate SLAs to clients. So we don't want to do that.
Just a quick question. I know you did speak to the alerting system and how y'all really didn't touch it, but I was wondering if you had any research on it or any sort of useful information for those of us who run too small of an environment to have someone 24/7 human monitoring for escalations and that nature.
So our alerting policy is pretty simple. We suppress alerts except once every 24 hours. We don't use escalations or anything else. We basically say it's once a day is enough to nag us. If we miss one alarm, we'll get it tomorrow. And if it's critical, it's going to humans who are going to escalate via a phone tree. Nagios supports arbitrarily complex alerting systems. It's a binary call out which you pass variables to. It can be arbitrarily complex. All of our logic is going in on the agent side. The agent doesn't generate the alert unless we want the alert to go out. There are other people I know I was talking with earlier who actually are doing it on the server side where they actually manage the alerts via more complex rules. We put all the logic on the front end and just don't worry Nagios about it if it's not supposed to happen. We change the priority on the client side rather than managing the alert pattern on the server side.
You mentioned that Nagios, or I'm sorry, your CF Engine was tied tightly to Goldman Sachs database for all your instances. Could you discuss a little bit the mechanism you use to pull that information into?
Okay. So our configuration generation on the server side is actually different from the client side. In both cases, they pull from the same database, so they'll be consistent, but they're very different. The server side config generation is implemented as a CF Engine module. So it's basically just an arbitrary script, and CF Engine's basically just being the execution engine for it. And it manages copying in the templates and making sure the production CVS version is checked out and all the other stuff CF Engine does. But then we run custom code that takes this template file, which basically says, oh, look, here's a host group, FIC hosts, FIC production. To generate the list of hosts in the FIC production host group, query Confucius for all hosts whose maintainer is FIC SA, where the isprod flag is 1, where the production state flag is not pending install or pending decommission. And there are probably a couple more criteria I'm forgetting off the top of my head. And return that list. For each host in that list, then they all have the following service list. So generate all the services. And there's some automatic service dependency logic in the generation as well, so that if you have a ping service defined for that host, every other service depends on ping. Because if you can't ping the host, then alarming on the fact that you haven't gotten a load average update for 30 minutes is really not relevant. Just send the ping alert and suppress the rest. There's that's very environment-specific dependency logic we have in there. But generally speaking, it's just a simple template file. Think of it sort of like PHP for Nagios, I guess, where you have a simple file which has database callouts in it and some loop structures. On the client side, it's just a template file. We have, again, another custom in-house CF Engine module that given a master file with a class expression on the left-hand side and a config line with optional variable substitution on the right-hand side, generates the config file for that service. So we can say that all web servers, anyone in the CF Engine class web server should get the web server up check. And that would have a hard time syncing with the server, so what we really do is say the CF Engine expression is all web servers should get the check, but CF Engine sets that class based on the server having a host function of I'm a web server in the database. So it's all cascading class definitions.
When I last tried Nagios, it had alert suppression for things behind a router. But at that time, I couldn't get it to deal with a mesh network. It had to be a strict tree. What is your experience with that?
We generally don't worry about that too much. The only way you can do that is to have a service dependency on, which checks connectivity. Checking a given device isn't the problem is you're trying to have a dependency that isn't the one you actually want. You think you want a dependency on all the routers or at least one of the routers being up. What you really want is a dependency on the far network being reachable. So what you do instead is you monitor each of the individual routers, but you actually want to do a ping check or some other check to say the service processors on the switches, and then you need N of M logic involved. You need some sort of quorum, or if any one of them is reachable, the service is good. So it's a custom check, basically. It's a custom agent you have to write to do that sort of thing. The topology, the simple examples they give where they show network topology, they're really bad examples. What you need to have is that, take the example where there's a single hop between router A and router B, and ignore what they say and actually treat that as some kind of mesh where that service check, rather than being a ping of that one router, pings all 4 of them, and if any one of them responds, says okay. Well, more likely if only one of them responds, says warning, but not critical.
You discussed using the statistics data and analyzing that to see what the state of the service is. Are you guys looking at using the Holt Winters stuff and RRD tool to handle that?
No, we've not been looking at our RRD tool to do that. From what I've seen, the analysis in RRD tool is fairly minimal. And it's also just in the wrong place in our architecture. By the time it gets there, it's too late. It's not what we want to do. We aren't sure yet. We haven't done the work yet to know what statistical analysis we want to run.
Okay.
I've just been reaching out to the people in the firm and outside the firm that I know that have the stats background that I lack. I know enough to know that the naive approach is wrong.
Like Hewlett-Packard OpenView takes.
Sorry?
Like Hewlett-Packard OpenView takes. The standard deviation stuff just doesn't work in a time series.
Yeah. So I know what the naive approach doesn't work, but I don't know what the right answer is yet. And we're looking into that with people who are much better than I am at statistical analysis, because I know this much.
Okay.
So we've done something very similar to what you've done, but not using CF Engine. We use LCFG, and we've been working on this recently so that if I say this machine has a web server, we automatically get an instance on the monitoring host. So if I had a new virtual host, I get monitoring. If it's an SSL host, I automatically get the certificate check, that sort of thing. But we've realized one of the big problems with this is all it's monitoring is that the machine's doing what I put into the specification of the data. So if I put that the port is 703 or something, and the machine goes and sets itself as port 703, the monitoring system's going to tell me that, yeah, it's done that, but that's not the same as saying that actually my web server should really be on port 80 and that I've made a mistake. So it doesn't protect you against everything. You kind of need a separate specification of your business and what your business requirements are in some way that sort of sits separately from your configuration data.
So the issue is that this is a configuration management problem, not a monitoring problem.
Absolutely.
And so your configuration management system allows you to specify port 703 for that service. If that's not valid, your configuration management system should throw an error. Right. Pretty much. And if it is valid, then it's valid, and then whether it's valid for that particular host or not is a much harder problem, and basically requires a human to be involved. Or a better class system. Yeah. Everything can be solved by adding another layer of indirection. So
the point is, it's a sort of general. There are cases where you would want a web server to be on a non-standard port. So you're right. It's just you have to. I'm just sort of making the point really that the sort of business logic has to be in there as well as just a configuration logic. And the other one I was curious about was, do you do any sort of clustering and grouping? And if so, is that automatic? So like, do you have like a sort of DNS and dependent, say, the Apache service depends on the DNS service being up and that sort of thing within Nagios?
Not today. Nagios supports the service dependencies. We use some of them. Right now, we actually return different errors from the agents. Because it's not central, it's sort of distributed. If the web monitoring failure is I can't resolve its address, it's a web failure, but the error is not web server down, the error is can't resolve address. Now, that does mean we'll get 2 alarms. If we're monitoring the DNS servers, we'll get alarms for both. In our case, we don't run the DNS servers. So we don't monitor them because if they're down, we're like, great, they're down. I mean, what are we going to do about it? We probably should, and we're actually about to run our own DNS servers because they keep trying to run them on Ultra 60s or other crappy hardware that can't keep up with the query load our NetApp puts on them for netgroup validation. But it's just, again, our design decision is to put almost all the logic in the client. So in that case, we'd have the client do the dependency check.
Over on the client side, suppose it detects an alertable situation like a process is down. Did you ever try corrective action before doing the alert?
No. We looked into that, and in almost no cases is there a corrective action we feel comfortable taking automatically. Now, we have not rolled this out to do things like mommying processes. Oh look, we have an unreliable piece of software that we have to restart, and if it's down, we'll try restarting it up to n times and then cry. If we run into that situation, we fix the broken code. If we have code that has to be nursemaided to that degree, we have other problems. Now, in some cases, because of business realities, you can't get around that. But it supports it. The agent can do arbitrary actions. It's Perl. Sadly, I don't particularly like Perl, but it's what the app devs know and the SAs know, so that's what we used. So it's there and it's possible. It's just not implemented today in any of our current agents.
In order to read up the config files, do you hup Nagios or do you kill it and restart it?
We actually currently hup it, though we do a config validation first. The problem is, at least some versions of Nagios, if you tell it to reload its config file and its config file is invalid, it exits, which is unfortunate. So I think we're still SIG hupping it. I don't remember. We went back and forth a couple of times. I think we're currently hupping it. There was, I think we were hupping it, then we restarted it, then we went back to hupping it once we added the config validation step.
Okay, we've tried hupping it and had pretty poor luck, and a number of other people have as well. So we've actually been killing it and restarting it.
What version?
2.7, I think.
Yeah, I think it may have been fixed. We're running 2.9, and I don't think we're seeing that anymore.
Okay,
I know previously we had some issues with it, and we went back. I know we've gone back and forth between them a few times, and I just don't remember the history off the top of my head.
Okay, but you're able to actually deal with it in a high availability environment where you have other Nagios machines actually monitoring it,
yeah,
and not have heartbeat issues.
Yeah, we don't. It's because everything's a flow through for us. Again, we're not using obsessive compulsive service processing or obsessive compulsive host processing. We're doing it via the alert path, and it's a little easier that way, I think.
Thanks.
Very interesting talk, thank you. Your teaser on the statistics stuff without the slides, are you going to publish any information on that or make any of that available?
The stats code is the next piece we want to release, but it has a lot more work before it's really safe for public consumption. My background is in InfoSec, and I'm not willing to release code to the world in general until I know people aren't going. I'm not handing them a semi-automatic weapon, with auto foot aiming technology.
You are no fun.
So that is it's not as mature yet. It's planned to release it as possible, but I'm trying to get the rest of the monitoring code cleaned up first, and then that'll be the next thing I have to go in and wade through and make sure it has enough, rubber safety bits added to it.
I mean, I'd be just interested in seeing what you're doing in terms of what you did with RRD tool and the data that you're shipping out with the sample size stamp.
It's just all you're doing is saying what you publish the RRD type, gauge versus whatever, and the sample rate. That's all it is.
Okay.
I mean, the bad news is that it's RRD specific.
Yeah.
The client knows too much about the back end. But the good news is at least it is self-describing within that semantic set.
Okay, thank you.
Hi. It's interesting that you achieved scale and reliability by using queuing technologies and stuff. And I'm sure some of the systems at Goldman that you're monitoring use, TIBCO and stuff like that for guaranteed delivery and financial. Queuing is used a lot. I'm sure. What queuing engine did you use? Did you write your own? Is it open source?
MonQ is what I'm hoping to release. It's multi-threaded C. Think of it as a really, really stupid web server. All it is a multi-threaded program that accepts connections, dispatches them to the appropriate handler, enqueues the data, and there's a DQ thread writing to that named pipe as fast as it's allowed to, and with some performance condition variables to make sure it doesn't do infinite loops on empty queues. But
did you implement it that way because you love open source and wanted to make it releasable, or do you not have access to your TIBCO license, or? TIBCO's guaranteed delivery is interesting, and I'd like to use it for
These days
monitoring.
we're actually more an RV shop than a TIBCO shop. I think we're moving away from TIBCO. What it comes down to is the various things like RV and TIBCO, they're way too complicated. And having to run them in production, I trust them about as far as I can throw them. They do work, but they require a lot of care and feeding. Again, the more complex a set of features you support, the more fragile the service becomes. I wanted this to be as fast as possible and as dumb as possible. Other than, if it weren't for the fact that I had to parse the Nagios updates to make sure there weren't bad commands in there, the first version of this didn't know anything about the data format except if it had to be new line terminated or not. Keep it simple. Simple is fast. Well, I guess that's it.